Welcome back. I'm going to move that back. I need a little bit more space here. Okay, so we are looking at section 3.5 and 3.6. And in that lecture video, we talked about shear stress and shear strain and the modulus of rigidity. And we talked about Poisson's ratio and then the relationship between the shear modulus, the modulus of elasticity, and Poisson's ratio. So essentially at this point, we have quite a few little numbers of equations, but they're all very short. And the thing you still have to remember is that in any one problem, we could use this equation if we had 3 different cables. This is going to be for 3 different cables. They're going to have their own values. And so it becomes like a puzzle, which I think is kind of fun. Okay. So then we have, so these are for our normal. And what does normal mean? Okay, normal means that longitudinal, okay? We are stretching, we are pushing, okay? It's a pull-push. This is shear. This means that I have maybe a block, okay? And I have that shear force that's acting across the top, and it is going to cause shear strain. Okay, we might want to glue it down here. And then we have the relationship, this equation which relates it all together. So we are going to be focusing on this aspect in this first problem. Actually, I lied. We are not. We are going to be looking at Poisson's ratio in this problem. Okay, so let's look at Poisson's ratio. At the proportional limit, a 20 millimeter thick by 75 millimeter wide bar elongates 6.8 millimeters under an axial load of 4.8 kilonewtons. The bar is 1.6 meters long. If Poisson's ratio is 0.32 for the material, determine the proportional limit, the modulus of elasticity, and the change in each lateral dimension. Okay, so I like to have free body diagrams. And I have a bar. It's a bar. Okay, so it's going to look something kind of like this. And then it has kind of a width into the page. And we are applying an axial load. Okay, and it has a thickness of 0.02 meters. It has a width of 0.075 meters. Okay, it elongates, so we're going to end up with a delta here of 0.0068 meters. Okay, and it's originally 1.6. So our original length is 1.6 meters. Poisson's ratio is 0.32, and we have an axial load of 480 kilon times 10 to the third newtons. Okay, remember I'm kind of weird. So here's my picture. Here's my free body diagram. If we are stretching it to the proportional limit, then determine the proportional limit. So if we're stretching it to that, that's going to be that stress at the proportional limit. Okay, and I know that stress is going to be the force that takes us to the proportional limit divided by our original area. Okay, so I have a force of 480 times 10 to the third newtons divided by, okay, I need that cross-sectional area because this is the area that's cross-section of that force. So it's going to be 0.02 meters and 0.075 meters. And when I work this out, I'm going to get a stress of, okay, it's going to be a very big number. So I'm going to divide it by 10 to the 6th. Can you guys see that? 320 times 10 to the 6th newtons per meter squared, which is 320 megapascals. Okay, easy peasy. B, the modulus of elasticity. Well, gosh, modulus of elasticity is stress equals E times strain. I have calculated this. That was given as my force over area. Strain is change in length over length. I have a change in length and a length, so I can now calculate the modulus of elasticity. Stress equals E times strain. So we have 480 times 10 to the third newtons divided by 0.02 meters times 0.075 meters, okay, Newton per meter squared equals E times change in length, okay, strain is change in length, 0.0068 meters, divided by original, 1.6 meters. And now, if I cross multiply that over, divide by that, I'm going to get that my modulus of elasticity is a really big number, okay? It's going to be a really big number. And 75.29, and it was times 10 to the 9th Newton per meter squared. So E equals 75.29 gigapascal. Okay, now it says the change in each lateral dimension. So if I want the change in each lateral dimension, that is where I use Poisson's ratio. And Poisson's ratio is negative strain lateral divided by strain longitudinal. Or you could call it strain tangential. Remember that means and strain axial. Okay, so when I look at this, this is going to be, and I don't really like this one, I like to say lateral and longitudinal because I always think of longitudinal being along the long axis and lateral being on the cross section. Okay, so if I have this like so, then I have that strain, which is the longitudinal, and then I'm going to have the strain of the cross section, and that's my lateral strain. Okay, so how do I get there? Poisson's ratio is 0.32 equals negative. I don't know the lateral strain, we'll get that in a minute, but the longitudinal strain. What is strain? Strain is change in length over length. Strain is 0.0068 meters divided by 1.6 meters. That's going to get me my longitudinal strain. So now when I cross multiply, I'm going to get that my lateral strain is negative. And remember, we have that negative sign, so we're going to bring the negative over, cross multiply, and I get negative 0.0272. Okay, and what is strain? That is not the number I get. I can't read my little calculator over here. I get negative 0.00136, and we are looking at meters per meter or millimeters per millimeter. It doesn't really matter, okay? So this is lateral strain. Why is it negative? Why is it negative? Well, if my longitudinal is positive strain, because we are getting longer, what's happening to my cross section? This is going to be getting smaller. And I know that that's like with contraction, so it should be a negative strain, okay? So how do we determine then our change in our lateral dimensions? Well, the same way we would longitudinally. Strain is change in length over length. So if I have a negative 0.00136 millimeters per millimeter equals, okay, the change in thickness divided by, what is my original thickness? 0.02 meters. So my change in thickness is going to be a negative number because it's getting smaller, and I get negative 0.0272 millimeters. Okay, so if I wanted to know then what was my new thickness, it would be 0.02 minus, okay, 0.02 minus, and apparently, yeah, millimeters. So it would be the 20 millimeters that I started with, 20 millimeters minus 0.0272, and so I would get a new thickness of like 19.9 something, okay? Now we can do the same thing. So that was for our thickness. Let's do the same thing, but for our width. So I have negative 0.00136 millimeters per millimeter equals the change in our width, and our original width is 0.075 meters. Let's make that back into millimeters. It makes more sense if we have this in millimeters. 75 millimeters. So our delta width is negative. Remember, it's getting smaller, and we have that negative sign in there. Negative 0.102 millimeters. So that's my change. So if I wanted to know the actual change in width, it would be 75 minus that, and I would get the new width of like 74 point something. Okay, so they got smaller. That's why the negatives are with the deltas, because when I add that then, what is delta? Delta is length final minus length initial. So length final equals negative delta plus L naught. So it's going to make it shorter. Okay, there you go.